Welcome to the Explainer. We're skipping the usual long intro today because we need to immediately deconstruct the absolute most critical Cambridge IGCSE computer science exam traps. We're going to look closely at the exact places where students are literally throwing marks away. So let's get straight into it and secure those top grades. All right, let's dive right into our first trap. Now, this is a seemingly simple 8-bit binary conversion, yet 9 out of 10 students are unknowingly throwing away guaranteed marks here. It's crazy. They walk out of the exam room totally confident, completely unaware that a tiny procedural error just quietly cost them their grade. Let me show you exactly what this mistake is, so you don't make it yourself. Look at this. Here's where that catastrophic right-to-left error happens. Students often mistakenly calculate their place values completely backwards, starting their power count at 2 to the power of 1 on the right instead of 2 to the power of 0. Doing this misses the least significant bit entirely. The result? A completely broken final denary answer that's usually off by just 1. And bam, just like that, the calculation mark is gone. But here's the thing you have to remember. Examiners reward your method. Once you see where that error creeps in, doing it the right way becomes almost impossible to forget. So, by always identifying your most significant bit on the far left first, the one with a value of 128 in an 8-bit system, you instantly secure your place value table structure. Even if you make a tiny addition error later on, having that correct table setup often secures those vital method marks. So to rebuild this correctly and beat the mistake in real time, you just need to follow 3 simple steps. Step 1, always draw the place value table out completely. Step 2, find the largest power of 2 that fits into your denary number for subtraction and place a 1 in that column. And finally, step 3, look at every 1 in your resulting binary string and just sum their corresponding place values together. This exact method is what the examiner is looking to reward. Okay, moving on to section 1, logic and programming structures, the zero iteration trap. This right here is an area where rote memorization just completely falls apart if you don't actually get the underlying mechanics. Take a look at the while loop. It acts as a precondition gate. So if that input stream where x equals 0 evaluates to false right at the very start, the code inside is bypassed completely, meaning the loop might literally never run at all, giving you 0 iterations. You really must remember that while loops require that first input to be placed outside before the loop even starts, just to provide a value for that very first check. But on the flip side, look at the repeat until logic. That's a post-condition loop. It guarantees the code processes at least once because the condition isn't checked until the very end of the loop exit. Honestly, choosing the wrong loop for a menu or a totaling algorithm is a classic way to lose your logical flow marks. Now, before we even think about touching a specific programming language, your algorithmic logic has to be absolutely ironclad. And you achieve this by using pseudocode first. Standard methods of solution, things like keeping a running counter or totaling values by adding to them every time an action occurs, should always be mapped out in pseudocode. It lets you focus purely on the logic, right? No stressing over language-specific syntax errors just yet. Okay, once that pseudocode is solid, translating it into an environment like Microsoft Visual Basic requires absolute technical precision. You need to know exactly which data type to call upon. For instance, distinguishing between high-capacity strings, which hold words enclosed in double quotes, versus a single-character char data type, which actually cannot be used in mathematical calculations. Precision here? That's exactly what separates a good student from a top-tier one. All right, let's pivot to section 2, hardware, networks, and systems, real-world applications. Shifting our focus to physical architecture, notice how the central hub in a star topology acts as a repeater for data flow. Every single node has its own dedicated, point-to-point connection straight to that central switch. Now, this offers fantastic high performance, and it isolates failures. So, if one cable breaks, the rest of the network is totally fine. But it creates a dangerous single point of failure. If that central switch goes down, the entire network drops dead. Listen to the specific examiner feedback, guys, because it is absolutely vital. You will lose marks if you just recite textbook definitions of a star topology. If the exam asks about a hospital network, you have to apply the hardware mechanism to that specific scenario. Explain why isolated failures matter in a hospital ward, rather than just stating generic facts. You have to connect the dots for them. This 4-question self-check framework actually forces you to tailor those answers perfectly. When you're tackling questions about protocols, services, or web browsers, ask yourself, what is it? How does it work? Where is it used? And why? By framing your answers through this logical sequencing, mechanism first, consequence second, you progress from just using everyday language to the time-pressured, highly technical exam response that the mark scheme actually demands. Moving on, the fetch, decode, execute cycle is not something you can just rote memorize. Using a triple pass revision strategy ensures you first define the mechanism clearly, then rehearse the exact sequence, and finally anchor it to a scenario. It is simply not enough to just name the CPU registers. You need to explain the logical sequence of data flow in a way another learner could easily follow. Which brings us to Section 3, Data Representation, the 10-second challenge. A huge part of this exam comes down to spotting invalid data while under pressure. So let's do a quick challenge. You have just 10 seconds to mentally process this scenario. Think about the difference between normal, abnormal, boundary, and extreme test data within a sound sampling context. Where exactly does a system with an 11-bit analog-to-digital converter fail? Lock in your answer. Time's up. The distinction here is super strict. Boundary data tests the exact edges, literally the absolute maximum accepted value before failure. But extreme data pushes past that. It tests the limits just outside the system's capacity, such as a frequency slightly higher than what that 11-bit converter can physically handle. Understanding this exact distinction, that is how you secure full marks on validation and testing questions. So building your overall exam defense really comes down to these core pillars. Always identify your most significant bit first to save your binary conversions. Remember to use while loops carefully to avoid those zero-iteration traps. Always apply your hardware and topology answers to the specific scenario they give you, and rigorously test your data boundaries. Master these, and you are well on your way to a top grade for sure. As you prepare for your papers, ask yourself, are you still falling for these predictable traps, or are you ready to use this visual mechanism-first approach to genuinely ace the exams? If this explainer made things click for you, don't wait. Apply these strategies to your past papers today. Keep focused, keep visualizing the logic, and I will see you in the next explainer.